of the concepts in it. Part of what makes it hard is that there's this first thing we're going to learn. You have to be a pretty visual learner, and if you're not a visual learner, it can make it a little bit harder. So I'm going to show you two ways that you can look at it. One way is visually, and I've already started by color coding and putting this on the board to kind of go over it with you up here to try to help you see it. And then if you still can't see it visually, then I'll show you kind of more of a step-by-step way that you can do it. But we're going to go out of order of our notes just a little bit. Before we get into what is this whole section about, I want us to skip ahead to geometric mean, because it's going to make more sense if you understand what is geometric mean first. So we're going to go to geometric mean first. If you'll flip in your notes and find this slide where you see the definition for geometric mean. Okay? So basically all last chapter we wrote proportions. That looked like a fraction equals a fraction. And in that proportion, we cross-multiplied and we solved for x. So in this situation, if I cross-multiplied, what would I get when I cross-multiply here? X squared. What would I get when I multiply here? A times b. So we would get x squared equals a times b. If I wanted to solve for x, what would I need to do next? Take the square root. So I'd take the square root, and I would get x equals the square root of a times b. Is everybody okay with that? So basically what they tell you here in this big paragraph is when you have a proportion, in that proportion there are two diagonals. The diagonal that goes down from left to right and the diagonal that goes up from left to right. We give those a specific name. So the one that goes up from left to right is called the means. And the one that goes down from left to right is called the extremes. And it's not important that you memorize that at all. But what I want you to understand is in this reading of this, when you read it, it says that notice that the number is the geometric mean of the extremes. So I'm going to go back through this and read this again. It says consider this proportion. In this case, the means, so you need to know what are they talking about when they say the means. They're talking about this diagonal. The means of the proportion are the same number. So do you guys agree that that diagonal has the same number here and here? So the means is the same number, and that number is the geometric mean of the extremes. So when they talk about the geometric mean, when they talk about the geometric mean, they're talking about the number in a proportion that would be the same number in those two spots. And the way you find that number is by multiplying the extremes and then taking the square root. So if I want to find this number, if it's the same number, I'm going to multiply these two numbers like we just saw, and then I'm going to take the square root to find that value. That's the definition for the geometric mean. The geometric mean of two positive numbers is the positive square root of their product. What does product mean again? Product means to multiply. So what they're saying is if you want to find the geometric mean between two numbers, so for example, let's say my two numbers are 2 and 8. And they say find the geometric mean between 2 and 8. The long way to work the problem would be to put 2 in one of these spots and 8 in one of these spots, and to put x in these spots. The geometric mean between 2 and 8 is the number here between those two extremes. And then you would just solve. Cross multiply, you just told me that would give me x squared equals, cross multiply, what do you get? 16, and then what do? Square root, and so x is equal to 4, and they said it's the positive square root. We've talked in here about how you're supposed to remember to put plus or minus. but it's only the positive square root. So you could do this, but that's the long way, or you can just memorize that the geometric mean is just the product and then the square root. So take 2 times 8, multiply, you get 16. Take the square root, you get 4. So geometric mean is just the square root of the product. The square root of the product. So for example, if you look at this next one, it says find the geometric mean of each pair of numbers. If necessary, give your answer in simplest radical form. That means do not round. So if they say find the geometric mean between 5 and 30, one more time, the long way would be to write a proportion. 5 and 30 would go in each of the extreme spots. X would go into each of the mean spots, and then you would cross multiply. Or the shortcut would be just to simply say that the geometric mean is equal to the square root of 5 times 30. So it's just the square root of their product. Multiply, take the square root. Okay? And again, we would get there if we cross multiplied here. X squared equals 5 times 30. Then we took the square root. X equals the square root of 5 times 30. But this is the long way. This would be the shortcut. Questions so far? Is this making sense what I'm saying? Okay, so then at this point, you can check to see, is 5 times 30 a perfect squared number? What's 5 times 30? 150. If you take the square root of 150, does it give you an exact value? No, so then you can't use your calculator at this point. This goes back to what we did before when we simplified square roots. You can take your calculator to check to see if it's a perfect square like 16. That's great, but if it's not, then you have to put your calculator away and you have to factor. What does 150 factor into? 5 and 30, which we already know from up above. Keep going. What does 30 factor into? 3 and 10. Keep going. What does 10 factor into? 5 and 2. So we've got a 2, a 5, a 3, and a 5. What are we looking for? Pairs. Do we have a pair? Okay, we have a pair of 5s. So where does that go? Outside. And what's left underneath? 6, because we have a 3 and a 2, and this is all multiplication, so it's 3 times 2, which is 6. So what we're saying is the geometric mean between 5 and 30 is 5 square roots of 6. Okay, so one more time. If I want to find the geometric mean between two numbers, what do I do with those two numbers first? What's the shortcut? Multiply them. Then what do? Take the square root. Quick shortcut, easy. If I give you two other numbers, let's say 3 and 12. What am I going to do to find the geometric mean? Multiply them. What's 3 times 12? 36. And then what am I going to do? Take the square root. So the square root of 36 is 6. Everybody okay with quick shortcut geometric mean? Okay, but understanding that the geometric mean occurs when you have the same number in one diagonal of a proportion. That's when geometric mean occurs. Yes, sir. Do you have a question, Thad? Okay. Okay, so why I went over geometric mean is because what we're going to learn today connects back to what we just did in Chapter 7. We're going to talk about similarity in right triangles. And when we do that, we're going to end up with some proportions where this turns out to be the same number in both spots. And so what we're really going to be calculating is the geometric mean. And I'm going to show you a long way you can work the problems or a shortcut way. And the shortcut way is using geometric mean. And if I were you, I would use the geometric mean shortcuts, but it's going to cause you to have to memorize. Whereas if you don't want to memorize, you can do it the long way. Okay? So, first thing we're going to start with is the entire lesson today starts with you have to have a special kind of triangle. So if you look at the very beginning of this set of notes, you should have, do you have this slide? Okay. You have to have a special kind of triangle. Angela, put your phone on my desk, please. You have to have a special kind of triangle. That kind of triangle is, it has to be a right triangle. What we're learning today only works if you have a right triangle. If you have a right triangle, and in that right triangle you have an altitude drawn from the vertex of the right angle. So I want to stress this over and over again. What kind of triangle do you have to have today? A right triangle. And then specifically in that right triangle, you have to have an altitude. This goes back to chapter 5. Altitudes go perpendicular from the vertex to the opposite side. You have to have an altitude drawn from the right angle to the opposite side. If your picture does not have a right triangle with an altitude drawn from the right angle, then what we're learning today will not work. Okay? But when you have a right triangle and you draw an altitude from the right angle, how many triangles are now in the picture? Careful. 3. There's the great big one. Does everybody see the big one? And then there are 2 small ones, right? And in those 3 triangles, what kind of triangles is every triangle going to be? A right triangle. The great big one's a right triangle. There's a right angle here for the second triangle, and then we know that means this has to be a right angle also, right? So this is also a right triangle. What happens when you have a right triangle with an altitude drawn from the right angle? Here's my right angle here. My altitude goes down from that right angle. It creates 3 right triangles. And in those 3 right triangles, they end up being similar. So do you remember last chapter there were 3 shortcuts we learned to prove that triangles were similar? One of those only required angles. What was our shortcut that only required angles? Angle, angle, similarity. So if you look at this picture, I'm going to show you how these triangles are similar. And what you're going to have to do, the very first thing on the homework, very first thing in the notes, you're going to have to be able to do is you're going to have to be able to write this similarity statement correctly by looking at this picture. So I'm going to try to show you 2 ways you can do that. But the first big idea is if you have a right triangle with an altitude drawn from the right angle, Vasai, stand up if you need to, you're going to end up with 3 similar right triangles. And here's why you're going to have 3 similar right triangles. So first of all, I have redrawn the black triangle here, A, B, C. Does everybody see how I took that triangle and basically turned it down? Can you visualize that reflection down? Because it's important you can see it visually. So now A is up here, B has come down here, and C is at the end. Everybody with me? Okay? Then what I did is I took this red triangle, and would you agree that this angle A in the big triangle is the same angle A in the red triangle? Does everybody agree with that? What property says that if they share a common angle, it's congruent to itself? Reflexive property. So this angle is going to be congruent to this angle because of the reflexive property. There's a right angle in the red triangle, and there's a right angle in the black triangle. So do you see that we have angle, angle, similarity? Everybody with me? Okay. So I took this red triangle and I turned it so that the angle A's were in the same spot. So what I did is I took this triangle and I basically flipped it down and then over, so that the right angle ended up down here, angle A ended up here, or maybe you can think about it as rotating it down. I rotated it down so that B is down here. That way I have the angles that are the same in the same location. Can you visualize that? Okay. Now I'm going to look at the green triangle and the big black triangle. Would you agree that in the big black triangle and in the green triangle that this angle C is the same angle? So this angle C is congruent to this angle C. Do you see that? And so now the black triangle and the green triangle would be similar by angle, angle, similarity. They both have a right angle. They both have an angle C that's congruent. So the black triangle becomes similar to the red triangle, the black triangle becomes similar to the green triangle, and therefore they are all similar to each other. To get this green triangle, I just basically brought it straight down so that the angle C's were in the same spot, the right angles were in the same spot, and then we have this extra angle B up here. So when I look at this picture, one way you can come up with this similarity statement is to redraw the three triangles so that their corresponding angles are matching up. Big to the one on the left, big to the one on the right. Then it's easy to write the similarity statement. ABC is going to be similar to ADB, which is similar to BDC. For some people, they have a really hard time, though, going from this big picture to these three pictures. So if you're not visual, here's another way you could do it. Okay, so I want you guys to follow along. I'm going to rename this big triangle a different way. So Reuben, don't name it ABC. Pick a different name. CB, okay, that's fine. CBA. Okay, so Reuben's naming it CBA. So let's say I don't draw these three pictures. I'm having trouble. I can't see it. I don't know how to turn them, flip them, rearrange them. So instead, what I can do is I can look at triangle CBA and I can start with the right angle. Which angle is the right angle in the great big triangle? Angle B. So I'm going to put a little right angle underneath here. That's going to tell me that if these three triangles are similar, their congruent angles have to go in the same spot. So when I name these other triangles, I have to make sure and put the right angle in the middle. Right angle, right angle. Okay, and I'm going to call this triangle 1 and this triangle 2. So here's triangle 1. So everybody look at triangle 1. What's the right angle in triangle 1? D, right? So that means D has to go here. I'll do triangle 2 in a minute. Does everybody follow that right angle D goes in the middle because right angle B is in the middle? Okay, then the second thing you can do without drawing the pictures is to look for the angle that they have in common by the reflexive property. I'm going to call it the reflexive angle. So when I look at the big triangle and I look at the red triangle, what angle did not change at all? Notice B got cut in half or cut in two. C is not even in this red triangle. So what angle did not change when I drew the black triangle and I drew the red triangle? A. A is exactly the same in both. Does everybody see that? So that means I'm going to call this my little reflexive angle. That means A has to go in the same spot over here because it's going to be congruent to A. And now I look at the red triangle and I just list the only letter I haven't used. I used D, I used A. What other letter is in the red triangle? B. You with me so far there? Let's try it with the green one. So again, we're going back to the big black one and now the green one, triangle 2. In the big black triangle, we already said the right angle was angle B in the middle. So in the green triangle, what's our right angle? D. Now be careful. The reflexive angle is not the same angle when you switch to the next triangle. So A was the reflexive angle for the red one and the big one. What's the reflexive angle for the green one and the big one? C. So where is C when Reuben named the first triangle? C came first, right? So this is the reflexive angle for triangle 2. This is the reflexive angle for triangle 1. So we're going to put our reflexive angle for triangle 2 in the same spot here. So since C came first, C is going to come first. Are you with me? Because corresponding angles have to be in the same location. So now I'm going to call this triangle C, D. What letter have I not used? B. So your goal right now, there's 2 examples, is to come up with the similarity statement for the next 2 examples. You can either do it by redrawing the pictures, or you can do it by comparing right angles and reflexive angles. So let's try the next example, you by yourself or with your partner, and then we're going to check it. And if we're having trouble, I'm going to show it both ways. One, by drawing the pictures, then I'll do it by comparing the actual angles, and you decide what works better for you. So first I'm going to start by drawing this big right triangle, UWV. So UWV, UWV. I'm redrawing it so that angle W, this right angle is here, so I'm just taking it and turning it this way. Everybody with me there? Now I'm going to redraw the red triangle. When I redraw the red triangle, which angle is exactly the same in the red triangle and the great big triangle? U. So everybody agree that this angle does not change at all in the red triangle. So since U's at the top, when I redraw this red triangle, I want to draw it so that U's at the top. So this is U. What's my right angle in the red triangle? Z. So it's UZW. That? Sure. The order in which you name them doesn't matter. What matters is the order in which these letters are matching up. Okay? All right, now I'm going to draw the blue triangle. What angle is the same in the big black triangle and the blue triangle? V. Does everybody agree that this angle does not change in the blue triangle and in the black triangle? So when I named the black triangle, angle V was down here on the right. So when I draw that picture, I want to draw it so that angle V is down here on the right. So V is going to go here. This is my right angle. What's my right angle in the blue triangle? Z. And that means this angle at the top is what angle? W. Okay, so V and V are congruent. And then U and U are congruent, and they all have a right angle. And if you can see it visually like this, then you can just go around and name it in the same order. So triangle, somebody name this black one the way you named your black one. Okay, so V, U, W will be similar to, so I went here, here, here. So that means it's going to be similar to triangle, W, U, Z, which is similar to triangle, VWZ. Now, as Thad said, it doesn't matter which order you named each of these triangles in, but what does matter is that your letters are in the same locations. So did anybody name their black triangle something different than VUW? Go ahead, Tate. Okay, so I'm going to rewrite it to show Tate what his should look like. So you said triangle UWV. So UWV should match up with UZW, which should be similar to triangle WZV. So that's the order. Somebody name it differently than these two. Go ahead, Reese. So triangle VWU. So you went VWU, so that should be WZU. Should be similar to triangle VZW. If yours is not like this, then we need to work on doing better at naming them. Another way to do it if you're having trouble visually, how many people are not seeing how to draw the triangles? Be honest. Okay, kind of, sort of. Another way to do it is to compare your angles. So if you're having trouble, compare your angles. Name the first triangle any way you want. So Ruben, how did you name the first triangle? Okay, so I'm going to go with this one right here, okay? UWV. So when I did UWV, I know this is the right angle. So when I name the other two triangles, since the middle letter is the right angle, these have to be the right angles in the other two triangles. A lot of students do okay with that. It's the next part that they struggle with. But make sure that you have your right angles in the same spots. Does that make sense what I'm saying? Okay. From there, you're comparing big triangle to the one on the left. So big triangle, one on the left. The angle that they have in common that never changes size is U. So since U came first, U has to come first when you name that triangle. So if we've used U and we've used Z, then that only leaves letter W for the end. Okay? Then go back to the big one and the one on the right. Don't keep thinking the first letter is the angle they have in common, okay? Go back and look at the big one. So big one, and the one on the right. The angle they have in common that never changes is V. So since V is at the end in that triangle, V has to be at the end in the next one. And then whatever letter you haven't used. So if you used Z, you used V, the only other letter you haven't used then is W. So you start by comparing your right angles, then compare what angle do they have in common that doesn't change, and then go back to the big one and the one on the right, what do they have in common that doesn't change? Okay, try the next one. Let's see if you do better on the next one. And I'm coming around this time, so if you have questions, you can ask me. So if you take try to draw the pictures or try to start by pasting the picture. Okay, write that down. Do you have a pencil or a pen? Okay, well there's one back here. You'll need a pencil for the words. There's a pen at least. Okay, let's see how you're doing. So again, I'm seeing different things. I'm walking around. I'm seeing some people who just have their similarity statement and they feel confident. They didn't draw pictures. They didn't write down right angle, reflexive angle. And then some of you are still kind of struggling. So again, visually, you can draw the great big right triangle first. And I usually always just redraw it so that my right angle is down here to the bottom left. So I took this triangle, I'm going to flip it over. That's going to make this J, this L, this K. Then I'm going to redraw the first triangle here on the left. The angle that they have in common when I draw a big triangle and I try the one on the left is what angle? K. K doesn't change. So that means when I draw the next triangle, I have to put K in the same spot. The right angle in the same spot. So what's the right angle in this first triangle? M. So that means this is K, M, J. Then I'm going to draw the triangle on the right. What angle does it have in common with the great big triangle that never changes size? L. So that means since L is in the bottom right-hand corner in the big triangle, when I draw my next triangle, L needs to be on the bottom right-hand corner. The right angle needs to be in the same spot so that our L's are in the same spot and our right angles are in the same spot. What is my right angle letter? M. So I have L, M, and then what's this angle? J. If you can draw the pictures, then you can just write the similarity statement using these three pictures. Nope, just the statement. If you have to have the statement correct. So however you can come up with it is up to you totally. Okay? So I'm going to start. Somebody tell me, how did you name the big one? Okay, triangle KJL then would be similar to triangle. We went top, down, right. So KMJ is similar to triangle JML. Did somebody name their first triangle differently? So triangle JKL should be similar to, you went JKL, so that would be MKJ, which is similar to MJL. Somebody name it differently than LJK. So triangle LJK. So you went LJK just backwards. So that would be JMK backwards, which is similar to LMJ. Questions? Okay, if you're still struggling, I need to help you one-on-one. So come into Encore today, come by in the morning before school, but let me help you get this more clear in your minds. We're going to move on. So why are we writing the similarity statement? What's the whole purpose in writing the similarity statement? It goes back to last chapter. If you had a similarity statement, then you could compare corresponding sides. And what did we learn last chapter about similar triangles and their corresponding sides? Not congruent, proportional. So what we can do, and I'm going to show you two special situations that will save us time. Worst case scenario, you forget everything I'm about to teach you right now. You can always write the similarity statement and then compare corresponding sides in your statement. That's the hardest and longest and not the easiest way to work it. Okay, so what I'm going to show you are some shortcuts. But here's where the shortcuts come from. So let's say that I'm only looking at the black and the red triangle. Would you agree that AC over AB should be the same as AB over AD? Do you guys agree with that proportion that I just wrote comparing corresponding sides? Okay, what do you notice about this diagonal? It's the same. And what we just learned is that if you have the same number in this diagonal, that's called what? What's the word? The geometric mean. And it's the geometric mean between these two extremes. And so what we just learned is that if I cross multiply here, AB times AB would be AB squared, and that would equal AC times AD. Are you with me so far? And if I wanted to solve for AB, what would I do? Take the square root. So AB would actually equal the square root of AC times AD. Agreed? Okay, so what they're going to say is let's look at what these pieces are in this great big triangle. So I want you to only look at the great big triangle right now. Great big triangle. So I'm going to redraw just this great big triangle with the altitude drawn because we're going to develop this little shortcut. A, B, C, D. Okay, what is AB in the great big triangle? What do we call a side of the great big right triangle? Say it again. Leg. Agreed that that's a leg? Okay. So what this is saying is AB is the leg. If I take the leg and I square it, this is our first shortcut we're going to learn. The leg squared will equal, now let's look at these parts. What's AC in the great big triangle? What do we call this whole side in the great big triangle? Hypotenuse. So the leg squared will equal the whole hypotenuse times, now look at AD. What is AD in the great big triangle? Great big triangle. AD is what? It's not a leg. It's not the whole hypotenuse. It's just part of the hypotenuse. And we don't know for sure that it's exactly a half, but we know that it's part of the hypotenuse. The part of the hypotenuse that it is the part that is touching the leg. So the leg squared will always equal the whole hypotenuse times the part of the hypotenuse adjacent to the leg. We're touching the leg. Okay? No, it is not necessarily congruent. It is not equal. Okay? This could be 2 and this could be 10. These do not have to be equal. These do not have to be equal, and therefore this does not split this into 2 equal parts. It just splits it into 2 parts. Okay? Just like in this picture, it's very obvious that LM and KM are not the same length. Okay? All right, this is your first shortcut. Write it down. If you did not write that in your notes, you are going to struggle with Chapter 8. Write it down. It is in your notes, but they do not write it like that, and it makes it a little bit harder to understand. So I'm going to show you where it is in your notes. Here it is in our notes, and it is this one right here. They write it like this, with no words. And so you just have to look at that and figure out what is A, what's B, what's X, what's Y, what's C. A is a leg. X is part of the hypotenuse that's touching the leg. And C is the whole hypotenuse, which is what we just wrote down. Do you guys see that? Okay, what I want to show you is that it works for the other leg as well. So here's the second one. Same shortcut. Would you agree that B is a leg? Okay, so the leg squared is going to equal part of the hypotenuse, but which part of the hypotenuse? The part that touches the leg you're looking at. So that's where Y comes in, times the whole hypotenuse, C. So in this triangle, either leg, when you square it, will always equal the whole hypotenuse times the part of the hypotenuse that touches the leg, always. So if I wanted to do this one over here, this would be the leg. It would be leg squared equals whole hypotenuse times this part of the hypotenuse. First shortcut. Second and last shortcut, I want to show you where this comes from. And again, worst case scenario, you have to go back and try to write the similarity statement and try to compare the sides. I promise you that's going to be the longest, hardest way though. Last shortcut I want to show you comes from comparing the red and the green triangles. So look at the red and the green triangles. Okay? Everybody's eyes up here. Don't tune me out. Don't zone off. Really important. Would you agree that AD over BD should equal BD over CD? Do you agree with that? Using this similarity statement? AD over BD should equal BD over CD. What do you notice right here? It's the same. So what is BD in this great big picture? Maybe you see it here. What is the BD part? The altitude. So what we're going to see when we cross multiply here is we get BD squared equals AD times CD. So our second shortcut, write this down, is, Ruben, hurry so you can write this down with us. This is important. Altitude squared, so BD squared, BD is the altitude, will equal, what is AD in this picture? AD is not the leg of the great big triangle. We're only looking at the great big triangle. It's just part of the hypotenuse, right? What's CD in the great big triangle? The other part of the hypotenuse. So the altitude square will always equal part of the hypotenuse times the other part of the hypotenuse. And those are your two shortcuts that you can now use to solve pictures for missing parts of the triangle. But only if you have what kind of triangle? with what drawn in it? An altitude. If it does not have a right angle up here, you cannot use this. If it does not have an altitude drawn from the right angle, you cannot use this. But these are two shortcuts that will work every time. Okay, I want to show you some examples where this is easier. So look at this first example right here. Everybody with me, taking notes, writing it down, paying attention. Hurry, gentlemen. Okay, so this is what you're going to have to be able to do. They're going to give you a picture like this, and they're going to say find X, Y, and Z. Do you have a right triangle in this picture? Is there an altitude drawn from the right angle? Okay, before we get started on this problem, I want to start with, in every right triangle, what is one theorem we learned a long time ago that we can always use if I want to find a missing side of a right triangle? What is a theorem that we've learned? Say it again. Pythagorean theorem. Don't forget that a squared plus b squared will equal c squared. But the problem is going to be here. Let's say I want to find x, and I look at this little right triangle right here. Can I use Pythagorean theorem to find x in that little right triangle? Why not? Because there's two variables. So you can't always do Pythagorean theorem because you may not have enough information. So you may have to use these shortcuts. So I'm going to practice the shortcuts, but I want to remind you that if you can use Pythagorean theorem, you're welcome to use Pythagorean theorem. It's not a bad choice. Okay, so for example, if I were to look at this triangle here, could I find z using Pythagorean theorem? Yes. Okay, so I'm not saying you can't use Pythagorean theorem, but you won't be able to work the entire problem with just Pythagorean theorem. It will not work. You will at some point have to use one of these shortcuts. So I'm going to work them only with the shortcuts to try to get you practicing that, and then on the homework you can decide. Would you rather use Pythagorean theorem or do you want to use a shortcut? So looking at this picture, let's start with trying to figure out which shortcut we have enough information for. So look at the picture. Again, you're only looking at the great big triangle when you're talking about a leg, and the great big triangle when you're talking about a hypotenuse, and the great big triangle when you're talking about the altitude. So what in the picture is the altitude in this case? 6. So we know our first shortcut is, or one of our shortcuts is, altitude squared equals whole hypotenuse times the part of the hypotenuse. Oh, I'm sorry. You're right. Thank you. Please stop me making a mistake. My bad. I was going to the first one over there. Altitude squared is equal to part of the hypotenuse times the other part of the hypotenuse, right? Okay. So let's see if we have enough information to use this shortcut. If not, we'll go to the next one. What's the altitude in the picture? 6 squared equals, what's part of the hypotenuse? 9. What's the other part of the hypotenuse? X. Do we have only one variable? Yes, so we should be able to solve this. If we had not started with this shortcut, we had started with a different shortcut, we may not have had enough information, and we may have had to go and look for a different way. All right, what's 6 squared? 36 equals 9x. What do? Divide by 9. And what is x? 4. The math shouldn't be very hard if you set it up with your shortcuts. It'll make it harder if you try to do similarity statement, compare your corresponding parts. Okay, we found x. Now we know x is 4. I'm going to add it into my picture. So now what do we want to do? You want to find y or you want to find z? Okay, if we want to find y, what is y in our great big picture? Is it a leg, an altitude, a hypotenuse? It's a leg. So we're going to go to our second shortcut. Leg squared equals the whole hypotenuse times the part of the hypotenuse adjacent to the leg. Means it's got to be touching the leg. Okay, so what is our leg in the picture that we're looking at? Y. So we're going to have y squared equals, what's the whole hypotenuse? 9 plus 4, which is 13. And what's the part of the hypotenuse that is touching y? Is everybody with me that it's 4? That 9 does not touch y? This part right here is not touching the letter y, but this part is touching y. So 13 times 4. Now we're going to solve for y. What's 13 times 4? 52. Y squared equals 52. What do? Take the square root, so y is equal to the square root of 52. Does it say anywhere around your answer? No. You cannot round unless it says to round. So what do we do today if it doesn't say to round? Factor it out. Simplest radical form. So what does 52 factor into? If you forget, go back up to what you just multiplied. What does it for sure factor into? 13 and 4. So there's going to be something right up above that's going to help you out if you don't know what it factors into. What does 4 factor into? 2 and 2. What about 13? Nothing, it's prime. So we have a pair of 2's. So what is y going to equal? Say it again. 2 square roots of 13. All right, now you have some choices. You know that y is 2 square roots of 13. You could do Pythagorean theorem if you want to on the great big triangle, because now you know this is 2 square roots of 13. You know the hypotenuse is 13 and you're looking for z. Or we could go back and use our shortcut. I'm going to practice the shortcuts because that's what we're trying to remember today. But you could do Pythagorean theorem if you wanted to. Okay? And I will work it if you need me to just to practice how do I square something like 2 square roots of 13. And we sure could. So Ree says, could we not just do Pythagorean theorem on this triangle using 9, 6, and z? And yes, you could. But again, I'm not going to do Pythagorean theorem because I want us to practice the shortcuts today. The more we practice those, the better we're going to get. All right, so what is z in terms of my shortcuts? Is it an altitude, a leg, hypotenuse, part of the hypotenuse? It's a leg. Remember, a right triangle has 2 legs and 1 hypotenuse. So z is a leg, so we're going to use this shortcut. Leg squared equals whole hypotenuse times the part of the hypotenuse adjacent to the leg. Okay, so what is my leg again? Z squared equals, what's the whole hypotenuse in the big picture? 13 times, what's the part of the hypotenuse touching Z? 9. Notice that changes depending on which leg you're looking at. Okay, what's 13 times 9? 117 equals Z squared. What do we do to solve for Z? First, we have to take the square root. So Z is the square root of 117. You can always check and see, is that a perfect square? Type it in. Does it give you a decimal? Yep, so now you have to factor. What goes into 117? Say it again. 13 and 9. And again, if you forget, just go right back up. They've got it factored for you, right? So Z equals the square root of 117. That factors into 13 times 9. 9 factors into 3 and 3 times 13. Pair of 3's comes out front. So we're left with 3 square roots of 13. Questions? Okay, I want to warn you about some math that I usually see done incorrectly. So if I were you, I would write this down. Let's say that you decide, I'm just going to do Pythagorean theorem as much as I possibly can. Again, I'm going to warn you, you cannot solve these problems today with just Pythagorean theorem. You can do parts of it with Pythagorean theorem, and then other parts you'll be stuck and you'll have to use a shortcut. But let's go back to this triangle where we have this. This is 13 for the whole hypotenuse, right? You guys with me? This part over here we found out was 2 square roots of 13. And let's say we chose to do Pythagorean theorem with this triangle. Very common mistake I'll usually see. So I'm going to do Pythagorean theorem solving this triangle for z. We know we should get this, right? So let's do Pythagorean theorem. A squared plus b squared equals c squared. What's going to go in for a? Z squared plus what's going to go in for b? Not 13. 2 square roots of 13 squared equals what's going to go in for c? 13. Remember, your hypotenuse always goes in for c. Okay, this is what I see students do wrong. The z squared plus, I see a lot of students that do the square and the square root and cancel it out and say 2 times 13 is 26. That's wrong. 2 square roots of 13 squared, you have to square the 2 and the square root of 13. What's 2 squared? 4. Times, now the square and the square root cancel, so we have 4 times 13. Or in your calculator, if you use it, you have to put it in parentheses before you square it, or it's going to do it wrong. If you do this, it's only going to square the square root of 13. So be very careful that you don't do this. Okay? Equals, what's 13 squared? Come on, guys, work with me. 169. Keep going. Z squared plus, what's 4 times 13? 52 equals 169. Subtract 52. Z squared equals 117. And now we're right where we were here. Do you see, though, that we got to z squared equals 117 a lot faster than trying to do Pythagorean theorem? These shortcuts are going to be easier than Pythagorean theorem most of the time if you'll use your shortcuts. Now, again, Reese was right. We could have used 9 and 6, which would have made that a little easier. But still, I would encourage you to try your shortcuts. Okay? Let's look at the next one together. I'm going to call on you and ask you to help me set it up. So be ready. We're looking at this picture. And let's go with Michael. What would we call V in this picture? Leg, altitude, hypotenuse, part of the hypotenuse. What is V? A leg. So in our shortcut, let's go with Vasai. What is our shortcut about the leg? Very good. And it's the part of the hypotenuse that is touching the leg, right? Adjacent to the leg. All right, so Brock, if I'm using that, what's going to go in for leg squared here? Nope, we just said, I just asked Michael, what do we call V? And Michael said V was the leg. And then I asked Vasai, what shortcut do we have that concerns the leg? And he said leg squared equals whole hypotenuse times the part adjacent to the leg. So what are we plugging in for the leg? V. V is your leg. Remember, that's what Michael just told us, that V was the leg. That's why we went to this shortcut that uses a leg. Think about your right triangle, Brock. If I have a right triangle here, this is the right angle. This is a leg, this is a leg, this is a hypotenuse. In a right triangle, you have 2 legs that make your right angle, and then the one across from it is your hypotenuse, okay? So V is going to go in for our leg. Trey, what's going to go in for the whole hypotenuse? Hold on, Trey. What's going to go in for the whole hypotenuse? W is not my hypotenuse when I'm looking at this great big triangle. Your hypotenuse is always across from your right angle. U is just part of it. What's the whole hypotenuse? Careful, when you have a part of something and another part, do you multiply them to get the whole thing? Nope, what do you do? Add them. So what's the whole hypotenuse? U plus 3. And then what is the part of the hypotenuse, Gavin, that is touching V? 3. Do you see that this is a problem if I start with this formula? Why is it a problem? It's two variables. You can start here, but now you're stuck until you either find U or V. So I can't solve this right here. I'm going to have to go find another thing that I can solve. So again, I'm going to go to my other variable here, W. Okay, what is W in this picture, Corbin? No, be careful, guys. Right triangle, big triangle. The hypotenuse is always across from the right angle. W is not across from that right angle. It's a what? Leg. So that means we're back to the same formula. So what's going to go in for the leg here? W squared equals, let's go with Caleb. What's the whole hypotenuse again? U plus 3. And now let's go with Matt. What is the part of the hypotenuse that is adjacent to W? U. Once again, do we have a problem? Yeah, so what I'm trying to show you here is you may look at your homework and try working a problem and get stuck because you can't work that variable first. There's 3 variables you have to find. You may not be able to find V first or U first. You may have to find what first? We couldn't find U first, or sorry, yes, we may have to find U first. We couldn't find V, we couldn't find W, so we may have to find the altitude or U first. We know the altitude's 9, but we may have to find U first, okay? So we couldn't find V, we couldn't find W, so now let's try to find U. When you look at this picture, there's 2 ways you could try to find U. One would be trying to do Pythagorean theorem with this triangle, but that's not going to work because you have a U and a W. So instead, what's our second shortcut that we haven't used yet? Altitude squared equals part times the other part. So part times part, and we're talking about the part of the hypotenuse, part of the hypotenuse. All right, what's the altitude in the picture? 9. So 9 squared equals, what is one part of the hypotenuse? 3. What's the other part of the hypotenuse? U. All right, now we finally have something we can solve. So when you get to the homework, if you get stuck, you write something down, you're like, I don't know what to do. Try a different shortcut. Try another shortcut. Look for Pythagorean theorem until you find one of the variables you can find. What's 9 squared? 81 equals 3U. What do we do from there? Divide by 3. What is U? 27. Now that we know U, we can go back over to both of these and plug it in, right? And we already have them set up, so we don't need to erase our paper when we're doing our homework. If you get to one where there's a couple variables, just leave it. Move over to another spot on your paper and keep trying to solve until you find one that works. Now you can just go plug it in. So V squared is going to equal, U was 27 plus 3 times 3. What's 27 plus 3? 30. So leg squared equals whole hypotenuse now is 30 times 3 the part touching V. So V squared equals 90. Take the square root, and V is equal to the square root of 90. That's not a perfect square, so we have to simplify. What does 90 factor into? 30 times 3. What's 30 factor into? 3 and 10. What's 10 factor into? 2 and 5. So we have a pair of what? 3's. And so that means V is going to equal 3 square roots of 10. 2 times 5 is 10. So now we have V. Go ahead and plug your 27 in for U over here and solve for W. change their mind. So we have W squared equals, whole hypotenuse now is 27 plus 3, and the part touching W was the 27. So W squared equals 30 times 27. W squared equals what? 810. Take the square root. Is that a perfect square? No, so we have to factor it. What does it factor into? Okay, again, you can always go back to what you just multiplied. 30 times 27. What's 30 factor into? 3 and 10. 27. 3 and 9. 10 factors into? 5 and 2. 9 factors into? 3 and 3. So do I have any pairs? I have a pair of 3's here. I have another pair of 3's here. And what's left? 5 and 2. When you have more than one pair, what do you do when you bring those 2 3's out front? Multiply. There is no plus sign anywhere. Everything's multiplication. Times, 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 times. Everything's multiplication. We never add. So this is going to become 3 times 3, square roots of 5 times 2, which is 10. So this becomes what? 9 square roots of 10. Questions? Okay, one more time, really fast before we stop, because we're not going to do that last one. It's just a word problem. It's the same kind of idea. You're just basically applying a picture to it and some words about the picture, but it's still the same kind of process. Really quickly, I'm going to draw a picture up here. I need someone to tell me what is one shortcut I could write down to solve for one of these variables in this picture. 7 squared equals very good. X times 3. Are you guys with Michael? Which shortcut did he just use? Altitude squared equals part times part. So when you look at that picture, altitude squared equals part times part. Altitude squared equals part times part. Okay? What if I told you this time that you had this information? What could we write down to solve for y? What is y? Sorry, this needs to be a right angle here. Y is the leg. Y squared equals 9 times 6. Okay? Leg squared equals whole times the part touching the leg. What would we write down to solve for z? Z squared equals 9 times 3. Are you getting it? Leg squared equals whole times the part touching the leg. Okay? Those are your two shortcuts. You got to be able to use them. Homework. This was the hardest lesson